Okay, go.
All right, hello everyone. I prepared a presentation for y'all. It's called Lessons in Equidecomposability. Now, you shouldn't be too intimidated by the word equidecomposability, but basically what it means is I'm going to be talking about dissection puzzles. And those things are like, uh, let me just, dissection puzzles are pretty much where you take a shape, it's like a bunch of pieces, and you gotta form different types of other shapes with those pieces. For example, this cat from this collection of pieces in the square. This is the tangram puzzle. You might have seen it before, but you can pretty much make a lot of shapes like animals or other like diamonds, whatever. The point is you can make a lot of shapes, and I wanted to explore this a little further and see like what exactly are the conditions for two shapes to be like the same piece-wise. Like for example, this square and this cat are the same. What other two shapes can be described in that way where two of them are the same? One question, okay, before I start the rest of this presentation is intuitively, what do you think? Is it possible to turn a square into a circle by just dividing it into pieces and rearranging it? So what I'm talking about is, let's say you have a circle, maybe you can like divide it into some number of pieces. Is it possible to like rearrange the same pieces by just rotating and transforming? Is it possible to turn those pieces into a square? Now you can use any number of pieces you want, just a finite number though. So let me know. You can like private chat me or anything. Just like, what do you think? Is it possible to turn a circle into a square? Maybe just give a brief, like one sentence justification if you like. But I just like to see, there is a correct answer, but I'm not looking for that. I just want to see like the basic intuition behind, say like, is it possible? Because I think there's rationale for both. I can just, all right. If you think about it, there are two ways to think about this. I mean, first of all, circles are, I mean, they're very curvy shapes. Like there's a lot of curve that it's not obvious to see that like maybe there's a way to somehow hide these curves by like combining them or somehow, but like it's really hard to think about a way to get to a square piece. But at the same time, you also have like a lot of pieces. So you could like make really small pieces where the curves like don't even matter anymore or something. And now you can rearrange it into a square, kind of like atoms. You just like rearrange it into this square. I mean, there are different ways to approach this question, and I think both are equally valid. We'll discuss this problem near the end. But for now, we're going to be considering a magic demonstration. And what I'm talking about here is we can turn a triangle into a square by dissecting it into just 4 pieces. Now, it seems pretty improbable. I mean, like the number of sides is different and like, the sizes. It's pretty hard to think about it. But this guy called Henry Dewdney proposed this dissection in which we can turn this triangle, this is an equilateral triangle, divide it into 4 pieces and get a square. Now let's just go through a couple details here. First of all, note that each of these pieces has a right angle. So like 2 right angles here, 2 right angles here, so that each piece will have a right angle. And those become, you kind of flip them around and then you get 4 right angles that are now able to be put together into a square. Now it looks like there could be some, editing tricks or something here, but it turns out this is actually a perfect square. And it's pretty amazing. I'd also like to show you the animated version of this, where you actually get, it's a hinge dissection. So you can animate this piece thing. So let me quickly switch screens while I pull up the hinge dissection. So the hinge dissection, real quick, looks like this. Let me share screen again. Take a look at this dissection. Let me wait for it to loop around, but pretty much this is what Dewdney was talking about. You can turn a square into a triangle into a hexagon, and so on. So from triangle to square is the simplest. You take those pieces and you can actually keep them together, like keep the points together so that it's kind of like hinged. This also works for things like square to hexagon, as you just saw there. And it's actually pretty mesmerizing how this works, how you can turn these pieces into like different shapes. Like, I mean, a triangle to a square, that's kind of crazy. I mean, if you think about it, you're taking 60-degree angles and then you're turning it into 90, and then you're creating an extra edge out of nowhere. It's actually a lot harder than it might seem. And I mean, this dissection is pretty much magic to me. But yeah. So maybe that can serve as a motivation for the rest of this talk. So let's continue. Let's quickly do a definition, a formal definition of equidecomposability. So that was the word I used earlier. It just means that we can cut a shape into finitely many pieces. These cuts can be curved, they can be whatever. These cuts should be of finite length as well. And the resulting pieces, we can rearrange it into the other shape. So what that means is two shapes are equidecomposable if one can be dissected into the other. So let me, again, let's go through some examples just to make sure we know exactly what this word means. Here we have a square. It turns out this square is dissectable into this right isosceles triangle. And it's actually not very hard. We can just cut it along the diagonal here, get two pieces, and then so we have now two triangular pieces. Now we just combine them, for example, along one of the legs, and then we can get this shape. And of course, this is just a rotated version of this. So then we can say that this square is these two, so square and this big triangle are equidecomposable. Some observations you might want to make about equidecomposability is first, it's like, think of it like the conservation of area, where you have two shapes. The pieces will have the same total area as the original piece. So the area of this and this must equal to the area of the whole square, right? And same for the triangle, the pieces must sum to this area. So it turns out from this observation that any two equidecomposable shapes have the same area, right? There's no way to get a shape decompose into some pieces and then end up with the shape of a different area, because all the pieces have to always sum to the same area. So we already saw a way to turn an equilateral triangle into a square. Maybe we can think about any triangle now. Is it possible to decompose any triangle into a square? So take like this triangle or this triangle or this triangle. Are these possible? Is it possible to turn these into squares? And we'll explore that right now. There is a way to turn triangles into rectangles. Maybe you guys can see it at this point, but basically, if you think about it, you have a triangle. The area of this triangle is what? Let's call this B, call the height H. Then the area is half BH. Now there are different ways to interpret this. One of them is if you take a rectangle inscribing this inscribing the triangle, then the area of this is BH, right? And the area of the triangle is then half of the area of this rectangle. So we can consider what happens when we half this rectangle along the midpoint. So the height is now h/2. We can see that the lower half of this rectangle is now bh/2. bh/2, which is exactly equal to the area of the triangle. So if we just draw on this diagram, if we consider this rectangle, well then this rectangle has the same area as this whole triangle here, the original one. So if we can find a way to take this top triangle and put it into these empty areas, then we're done. And that's actually not too hard to do because like you can almost see it immediately. You take this altitude. Now we have two pieces that will in fact fit in those empty areas. So here's the diagram for this. Once we do these two cuts, it's possible to take this, rotate it, and put it here, and take this piece and put it here. Quickly, we can consider the congruent triangles here because, well, these both have heights h/2. And by construction, since we divided this triangle by the midline, so halfway between this vertex and this line, that means that these two are equal and these two lengths are equal, which means that we can just call these two triangles congruent by, say, hypotenuse length congruence, and say that these are the same. So that means we can just put one here, rotate it 180 degrees, and plop it there. And now we end up with a rectangle, which is close, but not exactly what we wanted because we want a square. A square is a type of rectangle, but that doesn't mean we can always turn a rectangle into a square. So is it possible to turn any rectangle into a square of the same area? Because it's not immediately obvious. I mean, maybe the side lengths of the rectangle are really weird and it's just hard to turn that into a square. I mean, how are you going to cut this up in order to fit the square? Because one way, I mean, maybe we could like cut it like this along the middle, but then what are we going to do with this isn't the middle. We want it so that the side length here matches with here. So that can cover like the bottom bit here. However, but the rest of the square rectangle, you can't really cut it. Like it's gonna be weird still. It's gonna kind of look something like this. And it's like you can take this extra region, put it here, but this process is probably going to go on infinitely. And that is an issue. So maybe we need to think about this rectangle square matter in a different way. All right. So the question is, we need to divide this into finitely many pieces where the areas or the pieces can be rearranged into this square. So if this is B and this is H, yeah, we would need, since they have the same area by equidecomposability, that means that this length of the square has to be square root BH, which is usually bad if H and B are like arbitrary numbers. They're not very nice with respect to B and H. So maybe this is possible in very special cases. For example, if we had a 1/4 square, a rectangle, we could divide it along the halfway, and then we could just put this rectangle here, and then we'd end up with a rectangle with side length 2, base 2, and height 2. So this is also a square. So there are some cases where this is possible, but I'm asking for the general case where is it possible to turn a rectangle into a square? There's a really nice way to do this actually. So I'll just present it here. This one's also by Dewdney, but this is like reminiscent of one of those area paradoxes where you can like rearrange it and you get something of a different area. But this one's real, like there are no tricks here. What this diagram is showing is we take the square that we want here in gray on the left, so dashed. So we need to somehow transfer this area on the left to this on the top. And Dewdney figured out that, okay, we can fix the bottom like everything below this diagonal. We can keep it fixed. And then we need to turn this, so the rest of the rectangle into like the rest of the square. Like this area from this area. So now we need to figure out a way to do that. And they used, so Dewdney saw that, okay, we need to somehow take this piece, so the blue piece here, and move it up. So we need to slide it pretty much along this hypotenuse of the base triangle. And in doing so, we can fill the top region, and the remaining triangle will just slide down, kind of like leapfrog, where blue hops over green and fills in the remaining portion. So there are actually quite a few details that we have to make sure work. First of which is that, so let me just quickly draw another diagram. In this case, we need to make sure that when you slide it, this length here is the same as this length, because you need to make that equal. So let's just say in the original rectangle, the base is B and the height is A. So A by B. And we want to turn that into a square. We already figured out that the area of the square that we want is root AB. So how do we make sure that this length is possible? Well, by construction, I mean, we're moving this like, so we can draw this. Then we're moving this piece, so the one I'm going to outline in blue, up parallel to this base here. So we can consider this sliding motion. Well, then this needs to overlap with this. So these are actually equal. And then we also need this. So that's the first condition. So we can actually figure out what this common length is by using a bit of geometry. So we know the total length of this square is root AB. And we know the height of the square of the rectangle is BA. So this equal piece must be square root AB minus A. we're actually making a key assumption here, where this square is taller than the rectangle. And in order to do that, we just make sure A is less than B. So we rotate. So like if the rectangle is really tall, then we just rotate it on its side so that it's the square will be taller. So this is positive. Now what do we do with the remaining bit? I mean, what else do we need to make sure happens? Well, we know that the top piece, the top length over here, well, that has to be the same as this one because these two will coincide once you slide them. So we know this is root AB, so this is also root AB. And then that means that this remaining piece here must be, well, this is just B minus root AB, right? Simply because the total length was B. So we also know that B minus root AB is here. And we also know that it's positive because A is less than B. Pretty much I'm saying that this rectangle is shorter than the square, but it's like horizontally it's longer. So these are both positive. And now when we swap them, we need to figure out one last condition. And that is that, so if we look at this final diagram over here, this length is this length. So these end up in the same spots. So that means they have the same length. And if you look at the previous diagram, that was this length over here, the bottom of the blue one, and the top of the green one. So that's the last condition we need to satisfy, that the green and the blue will indeed match up when they're switched. So we take a look. So the remaining bit here was, so in this triangle, the top was B minus root AB, and the bottom here, we just got to figure out that. And in fact, since this is root AB, we know that this is also B minus root AB, minus root AB. So that means that we can, in fact, always do this. So these two are in fact equal. They're both B minus root AB. So when we switch them, like slide them over, these in fact will all line up. We can also verify a couple different things. For example, when we slide this up, this length and the right half, the right side of this small triangle, these will form the entire right side of the final square. And we can verify, well, that's A because that's the height of this rectangle, and the rest of it was root AB minus A. So they indeed add up to the desired side length. So all of this does in fact make sense. We can turn a rectangle into a square. There is one catch though, and we're going to talk about it here as well. What happens when your rectangle is really long, like this, where the base is much larger than the height? Well, then our square is going to look something like this. But that means that if we do the same cutting here, this value, like we're gonna, oops, what happened? Okay, we have this. Then, okay, the base piece is here. Well, then there simply isn't enough room for for the two pieces to switch. What I'm saying is, you see how these two had to match in this diagram? Well, now we can't make a cut where those two match because that's just simply gonna extend beyond, and we can't make a cut within our rectangle because this cut is simply too long. We can work out the conditions for which this happens, It's when this length here, which was root AB minus A, is greater than the remaining length, which we can look at here. That is simply A. This means that we can just solve for this actually. So root AB is greater than 2A. So AB is greater than 4A squared, right? We square both sides, and then we end up with B greater than 4A. So what this means is if the rectangle is more than 4 times as wide as it is tall, then this is in fact impossible. But we can actually, it's not difficult to fix this. So if we do in fact have a really long rectangle, we can kind of do a piling strategy where we have our rectangle. All we have to do is split it in half. Now we have 2 pieces that we can stack on top of each other and end up with a new rectangle. Now this rectangle will have twice the height and half the width. So in fact, the ratio between the longer to the shorter side decreases by 4 times. And that's good because if we keep doing this, then eventually the ratio of the longer to the shorter side will be less than 4. And then we can do, well, the rest of our dissection, which we did here. So it's actually possible to do rectangle to square for any rectangle. This is actually a very nice property because we'll be using it later. But what this means is we can turn any triangle, so any triangle, into a square. And the square, of course, has to have the same area as the triangle, but it doesn't matter what the triangle looks like. I mean, even if it looks like this, you might have considered this earlier, but if even if we have an obtuse triangle, we can do it. I mean, if you go back here, we see that this cut had to have been possible. And in an obtuse triangle, once we do that, I mean, the cut will lie outside, which is bad because, well, we can't make the cut anymore. But luckily, this problem is easily resolved by doing a different strategy. We just flip it like so that the obtuse angle is now on the top. And this guarantees that we can finally make that cut that we want. So pretty much any triangle can be turned into a rectangle, and any rectangle can be turned into a square of the same area. So we finally get that a triangle can be turned into a square. Now there's another observation that, okay, what if we have 2 different triangles? They have the same area, but they're not congruent. Well then, how do we turn this into this? Well, we can turn the triangle into a square, right, of the same area, and then we can turn that square into a triangle. This part is possible because equidecomposability is actually mutual. So if you have a shape that is equidecomposable with another shape, well then that this is mutual. So you can turn this shape into the other. Well, then we just reverse the process and we get the other way, and this shape is, so you can turn this shape into this shape as well. So it's mutual. So we can also turn squares into triangles. So therefore, this triangle and this triangle must be equidecomposable because they have a common like square. Also, this square is not arbitrary. It has to have the same area as the starting triangle, so this square is unique because it's determined by the side length. So, the side length will be the square root of the area of the triangle, so that the triangle and the square have the same area. Great. Now, this is all leading up to a very nice result in equidecomposability where it turns out that any two polygons of the same area are equidecomposable. And my goal is to show this to you guys. The proof isn't actually that hard because there is a constructive proof. It's very direct and it shows you exactly how to do it. So there is no doubt whatsoever. Let's consider first the easier case. And in fact, this is the case that we will be using. Polygon on the left, square on the right. Is it possible to turn this polygon into a square? If yes, then that means if we take another polygon, pretend this is a polygon of the same area as the original one. So, oops. We can turn that. Why does it keep? Okay, right. We have that, and we can turn that into a square of this. So an identical square. So pretty much goes here. Then we can show that these two shapes are equidecomposable because they can both be turned into the same square. So we will go through the process of doing that. We can get pretty close. We have the polygon and we divide it. So we know how to deal with triangles already. So it's very natural to take the polygon and turn it into triangles like so. We can always do this. So even for concave polygons like this one, it's possible to do it. I mean, there's a proof of this, but I'll just show you a construction. For example, this triangulation here. And what you end up with is a bunch of triangles. And you know what we can do with triangles? We can turn them into squares. So we simply turn each triangle into its own square. So we can almost turn a polygon into a square. What we're doing actually is the polygons into triangles into squares. But usually if the starting polygon is not a square or a triangle, then we're going to end up with more than one square, depending on how many triangles we cut the original polygon into, which is more than one. So now we end up with a lot of squares. It's not exactly what we want, but it's very close. And squares are pretty easily manipulable. So I suspect that the rest of this proof will not be that hard. I mean, we already have the squares, so it shouldn't be too hard to turn multiple squares into a single square. So now the question is, how do we turn this into the big square? Well, let's say the side lengths of the starting squares are A, B, and C. Let's just consider the two square example for now. So A and B. How do we turn these two into a big square? First of all, what is the area of this big square? Well, it's simply the sum of the squares. So the area of this square is a squared plus b squared because the area of this square is a squared, the area of this square is b squared. So somehow when you combine them with pieces, the remaining piece shape has area a squared plus b squared. And that might ring a bell because, well, a squared plus b squared, that must be the Pythagorean theorem. So we can take some inspiration. Hold on. What is not working? Anyway, we can take inspiration from the Pythagorean theorem and hold on. Let me erase this. We can take inspiration from the Pythagorean theorem and figure out how to combine two different squares into a single square. And we can do that using this method. One of the proofs of the Pythagorean theorem involves rearranging the pieces of two squares into a bigger square, which is kind of exactly what we want here. The construction goes as follows. you have the two squares, side lengths A and B. So we can put these in a bigger box, a bigger square, side length A plus B. And what happens here is, well, we want to construct a square that has area A squared plus B squared. It is not simply the area of this big square. As you can see, there is still some remaining area up here. In fact, it's exactly, we can label these now, but we have divided these sides into A and B. You can see that the extra area has area exactly 2AB because there are two rectangles of A times B. Now, what is this final square going to look like? Let me just draw it out. It's very nice, actually. You can take this square right here. So it's going to pass through this point, and this point. And this point is going to be on the bottom side so that this is A and this is B. So pretty much reflected a lot of this point. All right. So we can confirm that the area of this square is A squared plus B squared, but that's not actually relevant. We just want to find the construction. So now we can see that once we combine these, we have a big piece here. That is contained within both of these squares. And now we have two of these triangle pieces that I will draw here. Now you see that this big region will stay intact for this construction, but we have this very convenient extra region that we need to fill out. And lucky for us, now it's very easy. I mean, we take this and this, and we just move them over. So this one goes here, this one goes here. Each of these smaller pieces is it's an A by B right triangle, right? So this is always possible. We just take the A and B, transfer it this way, the other one, and transfer it this way. And we finally end up with a nice square with area A squared plus B squared. So we see now that it's possible to turn any two squares into another square of with the same area as the total. And that's good because we can just repeat this process for multiple. So if we had 3 squares, well, then we could just combine these 2 squares to get a bigger square, and then take our resulting square, say it looks like this. Well, then we can just do the same thing for these 2 squares and then end up with a big square. And we can do this for any number of squares. So we can turn any polygon into a bunch of squares, and we can turn those bunch of squares into a big square. And that is it. I mean, we have shown that we can turn any polygon into a big square of the same area. And that is enough to show that, well, any 2 polygons of the same area are equidecomposable with finally many pieces. This is the Wallace-Bolyai-Girwian theorem. And this is true because we just well, we have our triangle, or, well, any polygon really, but it can be decomposed into triangles. Turn that into a square, and then turn that square into the other polygon. And this is probably one of the most fascinating results I've seen. Like in all of math, this is just mind-blowing how you can turn any 2 polygons, no matter how complex, no matter how many pieces, how many sides it has. It's always possible to turn a polygon into another polygon of the same area. It's like, it doesn't matter what these polygons are, it's always possible. And I mean, the only condition is that they have the same area. So you can just, any polygon, take a pair of scissors, cut it up, turn it into a square, and then like glue it together or something, and then cut that up and turn it into the other polygon, anything you want, as long as they have the same area. It's pretty beautiful. And finally, the final question then would be, is this possible in general? Can we take any shape, including curved shapes like circles, and turn that into any other curved shape as long as they have the same area? I mean, it's very natural. If you have a circle, that's pretty much a polygon. It's a polygon with infinitely many sides, right? So we can very well approximate it with, say, a hexagon, a 12-gon, any number of sides, any like large number of sides, and we can pretty much get a circle. Can we turn that into a square now? Or vice versa, can we turn a square into a circle? These are equivalent, but you actually think about it differently depending on which way you're going. But anyway, can we make this equivalence between circles and polygons? Because if that's possible, I mean, I would imagine then any two shapes are equidecomposable as long as they have the same area. On the other hand, there is like a very specific curvature to circles. And it's really hard to remove that curvature by dissecting it into pieces. Like these arcs will always remain, even if you dissect it into a bunch of tiny pieces, anything. These curves will remain. And it's not very easy to see that, well, is it possible to get rid of these? Maybe, maybe not. Either way, we need to find a way or disprove that there's no way to turn the circle into a square, and that is the square circling theorem. So we know this is, anyway, this is an aside, but we already know that squaring a circle is impossible via compass and ruler, right? You take a square and make a circle of the same area as a square. This is a classic question. It's been proven that you can't do this with compass and ruler. So maybe that applies here somehow, that circles and squares are somehow like fundamentally different and you can't dissect one into the other. But let's just consider how this is going to work. So are these two equidecomposable? Can we divide this into pieces such that the square becomes a circle, or vice versa? And I mean, okay, you should probably stick to normal cuts, as in finitely many, finitely long cuts. So that is our constraint. And it turns out, with a bit of thought, that the answer is no. And let me just show you a quick demonstration of why this is impossible. This will illustrate a very important technique in Olympiads and proofs in general called the invariant. An invariant is something that does not change with respect to like some operation you're doing on it. Like if you had a like a very simple invariant would be if you had a some collection of numbers, say, hold on, 1, 2, 3, 4, 5. And then the operation would be taking any two numbers and adding them. So for example, we could take these two numbers and get the number 5 and consider the whole sequence again. Well, then the invariant is the total sum. So sum of elements. You can see that this number will always stay 15. 1 plus 2 plus 3 plus 4 plus 5. No matter how many times we perform this operation on, any two numbers, we can see that the total sum of all the elements will not change. So, for example, we can do it again. 195. Well, 9 is the same as 5 plus 4, so the total sum does not change. And so therefore, if you do this a bunch of times, it doesn't matter how you do it. you always end up with a number 15. That's just a very simple example, but it shows the intuition behind what an invariant is and how it can be really powerful. Because, I mean, like if something is invariant, then that tells you that no matter what you do with it, this value will always stay the same. And in this case, I'm going to be using the invariant total curvature. That's what I call it. I don't know what the actual name is, but I'll define it here. So over all pieces, let's just take, for example, the left piece. I'll make a cut along the middle as shown here. And I end up with this shape here. Now, I mean, there's some flat regions there, and there's some curved regions. I'll discuss 3 different categories. So let's just say the red. Let's say red is convex. So locally, that means that it's like poking out, as in, all right. With respect to the left shape here, can you see how this curve will be convex in this case? Because, I mean, locally, like, there is a very rigorous definition of this, but pretty much what it means is if you take 2 points along this curve, then the line connecting them will always be contained within this area here. And you can see that it's pretty much like jutting out versus something like over here where the same region is caved in. So we call that concave. And this is because we take a point here, take a point here, connect them, and now this segment is outside of our desired region. And we'll just call the region where this is true concave. So intuitively, one's jutting out, one's caving in. It's very intuitively, it's very simple, but it might get a little complex when you have like strange like things like this. But I mean, it's always possible. I mean, you can see that this part's like concave, like if you consider the whole thing, for example, this is concave, but then this part, it's like convex, and then it goes back to concave, and then convex, and then concave again. You can kind of see how it's possible to assign either blue or red to any point on this curve. And then, of course, there is the third case. This third case is just like flat. I'll call it flat, where it's neither concave or convex. It's just a straight line. So that means this portion is flat. Well, you can see that this portion is flat and this portion is flat. So let's color code so let me just redraw this. I just erase all of this. Well, then we can kind of draw. Hold on. All right. So we can draw this piece again over here. This part was flat. And then there's this concave region here. And finally, this is not to scale, and then you had a convex region here. So within this piece, this is going to be the color code that we're going to assign. But now let's look at the other piece. What happens here? Well, what was concave for the left piece is now convex. It's jutting out. I mean, look at it. This is the piece. Well, then it's sort of like jutting out there, and then it's caving in on the bottom. So you can see how every concave point on the left side must be a convex point on the right side, as long as they're along the same cuts. And this is true for, well, any number of cuts. You can even like make a third cut here well, then this is going to be convex on this side, but concave on this side. And pretty much what I'm trying to say is any cut you make in the solid, in the shape will form a pair of blue and red points. Or if it's a flat cut, well, then it's just, if you make a flat cut, for example, this, well, then these two are, of course, both flat. So the invariant that I propose here is black. Actually, we can just ignore the black, but because black contributes 0, but the total curvature. So I'm saying how out it is, so red, minus how in it is. And this is nice because every cut we make, this value is 0. So along every cut, the number of red, the amount of red, is the same as the amount of blue. Like we'll say like length. This isn't very rigorously defined in like other more complex cases, but for our purposes, length just means the total arc length of the blue and the red. So length of red, right, minus length of blue, right? Okay, and this value will remain invariant because every cut will produce a pair of blue and red segments that exactly cancel out. You can see here that for a square, well, that value is 0. I mean, you start with a square. It's a very flat shape. All the segments contribute 0. So this has 0 red portion and 0 blue portion. So this is 0 for a square. But let's consider what happens when we look at a circle now. A circle is all convex. And if you make a cut inside, it doesn't really matter what you do. Well, like you can, like these will always cancel out. Black goes with black, blue goes with red, red with blue. So the cuts don't make a difference in this invariant because red minus blue will always be 0 for a cut. Because you have two sides and the sides cancel out. So for a circle, this is some positive amounts, right? Circles have a positive amount of total curvature. And that's not good because we have a square that has 0 curvature and a circle which has positive curvature. And that means that if it is possible, like it is like completely impossible for this to happen because you have a square, you make some cuts, the pieces will still have 0 curvature total. And you can't change that. I mean, no matter how many pieces, however you rearrange it, it's impossible. You cannot, like, even if you combine two pieces, the region, the segment of the common segment will still cancel out. Like there's no way to change it to 0. So therefore, it is impossible to get a positive curvature from a square. No matter how you cut it, however you reassemble it, it is impossible. And it follows then that it is also impossible to form a circle. So this is actually impossible in all cases. And that pretty much concludes my talk, but I want to just do a very quick discussion of the 3D case. There was a very famous problem proposed by David Hilbert in 1900. This was one of his 21 or so problems that discussed, is it possible to do the same thing, but with any two polyhedra? Because, I mean, we already showed that it's possible to do it with polygons. Why not 3D polyhedra? And it turns out that it's impossible, which is kind of surprising, but it's true. There's a way to pretty much, someone found a counterexample. It's very simple. You have a cube, right? And a tetrahedron, and I mean, someone showed that these are not using invariants, these are not able to be dissected into each other. This is called scissors congruence. in the 3D case, but it goes to show that very simple ideas, like the ones I presented in today, can have very big implications in math. Like when you take general cases, it might just be like something major. For example, one of Hilbert's problems, I mean, not many of these problems are solved even to this day. And I mean, this was one of them. This was in fact the first one to be solved. But it just goes to show that you can generalize and get pretty hard questions. And yeah, this is why I'm trying to show that simple problems like this, I mean, these have been studied for like 2000 years and they're still super interesting. I mean, these problems are types of problems where, you learn a lot and they're very worth studying. Even if they seem simple, like simple questions are often the most instructive. So I just hope you took something out of today's talk, and I hope you go out and find more of these instructive, nice problems. Thank you.
Thank you, Adam. Let's see if people have questions. So, Adam, I have a quick question. Okay.
Yeah.
So, context of this. How did you get interested into this topic? Is it part of a project you did? Is it part of a course you did or a book you read?
Okay. Yeah, that's a good question. I have had a bit of experience with this topic, mostly just like with toys of like little dissection puzzles. I had a tangram at some point, but yeah, I just played with stuff. When I seriously got into this topic, like I started researching it and looking into it. That was like this summer, last summer. It was like July or so, and this YouTuber called 3 Blue 1 Brown, he had a summer of math exposition
So you
contest.
submitted as part of that?
Yeah. So I
Great.
pretty much submitted a video version of my talk to that. I didn't win, but I think it was a very fruitful experience for me because I learned how to, first of all, I learned a lot about the topic, but I just saw how important it was to study like these small mini examples of questions because they can have big implications in terms of both like mathematical knowledge and also just like thinking, lateral thinking in general. So yeah, and I also learned how to like describe and instruct other people in the same manner. So I definitely think that was a very meaningful experience, and that's why I wanted to present on this today.
So great. It's awesome that you submitted as part of that challenge. And if you have a link to that
Oh, of
video that you can
course.
share, that would be
Yeah, I'll
great.
send it right now, actually.
Okay.
Give me one sec. All right, this is it.
Okay, so anyone else has a question?
You want to see?
If no one else has a question, I will stop recording. Adam, thank you once more. It was very, very interesting talk and very well presented. I understood it.